I think Frank went to find her. Okay, so I think we can start. So today we have for the seminar we have Hamid Hassani, which is doing his PhD studies at the Alberta University, and before that he studied in Iran in Tehran University. And today he's going to talk about the FANGS James Webb study of compact sources in nearby galaxies. Compact sources at 21st micron. This is a very wide survey covering several galaxies with James Webb, MUSE, ALMA, and HST. So it's a very extensive survey. So, okay, whenever you want, Hamid, it's all yours.
Thank you so much, Juan. Hola, everyone. As ALMA is Spanish. So I'm super happy to be here. I'm Hamid Hassani, PhD student at the University of Alberta, working with David Kozlowski and a member of FANGS collaboration. So I'm going to present a paper today, actually a short letter, titled PHANGS-JWST first results, as John mentioned, the 21 compact source population. So I'm going to probably start with introduction and a little bit of giving more information about my city, which is going to be this. Oh no, I guess there are lots of snow here and there is no city at all. But yeah, this is Edmonton, Alberta, but with snow actually. So this is our city in province of Alberta. So as you might guess, in Canada, weather is so cold, you cannot compare that easily with Spain. So the typical weather for winter is like minus 40 degree or minus 30, and that is so that is so cold and close to the northern pole that you can see aurora easily in the city. Thanks God, I'm really appreciative of global warming these days. That city is getting warm and we have like temperature of 29, 30 degree, probably warmer than Spain and many other countries. And that's the reason we have like wildfire, huge wildfire. And the whole city is like orange and which is insane, which is totally insane. So yeah, this is Edmonton. Today I'm going to talk about this paper actually, which is part of a series of papers, which with the title of PHANGS-JWST first results, which published on February 2023. And so it was a paper. We published about 21 papers from the observation of JWST. And I should say that I'm going to talk about who we are today, and I'm going to ask a few serious questions and look at all of these gorgeous observations, and finally I'm going to answer a few of them if we have proper time. So yeah, who we are. So FANGS is a super weird name actually, I would say that, because it stands for physics at high angular resolution in nearby galaxies, and we study interstellar medium in short. So we are using different windows, wavelengths, all the way from optical to the radio continuum and the UV and molecular gas and millimeter actually, and everything except X-ray. So we use all different windows to observe and study interstellar medium except X-ray. And yeah, that's all from our job. So I should start with some really short introduction about what we do in FANGS actually, and what is the baryon life cycle. So as you know, we have all of these diffuse atomic gas in galaxies, like hydrogen atomic gas, which is like diffuse, and it's gonna be it's surround all of the galaxy, much like beyond optical disk of galaxy. 2 or 3 times beyond the optical disk of galaxies, which you can observe that with the spin flip of the hydrogen at 21 centimeter with radio telescopes. And on the other hand, you have dense molecular gas phase of the ISM, which you can, which is like the trigger of star formation and the fuel of star formation actually. And we can observe that with the lots of different methods. As you might know, that observation of the hydrogen molecule or H2 is quite hard in the interstellar medium. We use other tracers like CO or carbon monoxide with different transitions lines. And we use millimeter observation, particularly the ALMA or IRAM observation to see CO line from the galaxies. These dense molecular gas gonna be collapsed and create a fresh generation of stars that you can see in star clusters. And those star clusters are bright from UV to near IR continuum. And you can use variety of telescopes based for both ground-based and space-based telescopes to observe the near infrared. However, a few part of that UV you can actually observe UV from Earth, and that's the reason we use HST actually and other telescopes, Galaxy and AstroSat maybe, to observe UV from photosphere of stars. And on the other hand, after a few maybe million years, all of these star clusters gonna be create a complex of massive O1b stars that's gonna create the H2 regions actually, which is like ionized hydrogen, which is surrounded by lots of dust and gas. So you have lots of ionized gas with temperature of about 10 to the power of 4 Kelvin. And after a while, a few of these massive stars gonna be explode and enrich your ISM with lots of heavy materials. And you have lots of the dust around H2 regions. And you can observe actually this phase of ISM, this phase of form ionized ISM with ionized gas lines tracer like H alpha, Balmer H alpha, or radio continuum. So it's gonna be optical or radio continuum with radio telescopes. So after a while, all of these electrons, all of these separated electrons from hydrogens gonna be cooled and recombined and create all of the hydrogen atoms again, and you're gonna be a cycle of the baryon life in the galaxy. So this is gonna be, as long as you have this cycle, you have a like galaxy and you can have a star formation and see what's going on there. This is a very quite dense of what we do actually in PHANGS. As you can see, there is no X-ray study in PHANGS collaboration for now, but it's gonna be probably included in the next years as well. So I just want to also start, as we all of us, at least most of us at PHANGS we are observational astrophysicists. So I'm gonna just go and review in more details about different phase of star formation, different phase of ISM with actual pictures and observations. So this is the galaxy NGC 628 at a distance of about 9.8 megaparsec. So most of the PHANGS targets are between about 6 megaparsec to 20 megaparsec, and those are based on ALMA observation of 19 nearby galaxies from about 2 to 20, 30 megaparsec. So this is NGC 628, one of the phantom galaxy, as you might heard about that. You have the molecular gas we have a transition line of 2 to 1. You can see all of these dense clumps of gas and giant molecular cloud, which are like, as I mentioned, they trigger the star formation. So wherever you have like bright knots here, you will see star formation. This survey of the molecular gas is conducted by Adam Leroy from the Ohio State University a few years ago, and we have like 1 arcsecond map of the 19 nearby galaxy with ALMA. So we have like 12 meter array plus TP plus 7M of all of these galaxies. On the other hand, speaking of James Webb and dust grains, we have this gorgeous recently published of the dust and actually hot dust from the ISM. So this is the phantom Webb galaxy. This is all of them of the same galaxy. So we have PEH, which stands for polycitric, aromatic hydrocarbon, which are actually carbon-based molecules, and you have these are vibrationally vibrationally heated molecules that when you have UV bright, when you have intense UV emission from stars, these molecules gonna be heated, and you will have vibrational transition, and you will see all of these pH emission at a few specific bands like 3.3, 7.7, and 11.3, as well as dust continuum emission, which is because of the heating of dust grains from the stars. So you have dust window here. We had like molecular gas window here. On the other hand, as I mentioned, this is the warm phase of the ISM, 10 to the power 4 Kelvin, which you can easily trace that with recombination lines actually, such as H alpha. So we have MUSE VLT observation, IFU spectroscopy, integral field spectroscopy. So we have, as you might know, that we have a spectrum of every individual pixel of this galaxy from about 4,000 angstrom to 9,000 angstrom. So we can do lots of stuff with the IFU studies. Most importantly, we can identify H divisions with lots of different ways, including BPT diagram, which is going to be really important for my study, because it's important for us to understand the birth and the evolution of H divisions. So as you know, that we have O and B stars in the H divisions with mass of more than 19 solar mass, which is gonna trace star formation up to about 5 million years. So whenever we look at the H alpha, it's gonna be trace star formation about 5 million years. Which, on the other hand, when you look at the UV emission, you will have you are looking at the emission from atmosphere of stars from almost the same star, 1b, but they are like less massive, so about 3 solar mass. So you have emission from photosphere of stars for young stars actually, and it's going to trace star formation on a longer scale, like 100 megayears, which is going to help you understand star formation history on a long range. So as I did not mention, that the H alpha and the MUSE VLT observation of the FANGS is going to be limited to the optical disk of galaxy, because MUSE has a quiet small FOV, which is going to be which is actually great, a 1 arc-minute FOV for the wide field mode actually. So we have FUV emission. So the best setup or available UV emission right now in literature is from galaxies, which provide you about 5 arcsecond resolution of FUV and NUV. However, in FANGS, as a part of my PhD, we have like UV observation, which is from AstroSat telescope. AstroSat is a Canadian-Indian telescopes that we built together, and it has a quite large FOV, 28 arc-minutes. So incomparable with JWST, ALMA, and I don't know, or MUSE or any other telescopes, we have 28 arc-minutes that we can see all parts of the galaxy, including the outer part of the galaxy. So, and in addition to that, with the AstroSat, we have like 7-8 bands from the UV, which is like gonna help you to understand extinction curve properties. And finally, we have 2 other phases of star ISM, actually, which you can see that through atomic gas and optical, which is going to be trace the star formation again. And with the HEC observation, actually, you can see individual clusters at the scale of about 5 to 10 parsec in these targets. And finally, from VLA, we have like old kind of observation of these galaxies with 10 arcsecond to 15 arcsecond. And recently we started a recent survey of nearby galaxies with MIRI, which provide you radio continuum and the H1 line with a resolution of about 6 arcsecond. So this is the all data set we have from the galaxies, and every single study is led from different person in collaboration. This part is mine, and that I've started with the PhD with that, and it's going to be published soon. I'm going to go back to this part at the end of the presentation. So what is the questions that we have for today? So the most important question I'm going to ask is, what is 21 micrometer emission from galaxies? And we have a few previous observations in classification of sources with infrared in Milky Way. And I'm going to ask this important question that where and what are the 21 micrometer sources? Are they stars? Are they H2 regions? Are they stellar clusters? Or maybe if they are associated with molecular gas? What is the luminosity distribution of all of these targets? And finally, when we observe all of these targets, can we model the SED or spectral energy distribution to answer the most important question of like, what is the age and mass of stellar population if they are embedded or not? So galaxies at 21 micrometer. We know that the 21 micrometer, which is like mid-IR continuum of emission, mid-IR continuum emission of the galaxies, is originated from the stochastically heating of dust grains by UV photons, which will be emitted actually in a long range of the infrared from about 7 micrometer to 21 micrometer. And 21 micrometer is pretty important to understand two important relations here. First one is understanding Kinnicott-Schmidt law that most of you know, which is about the relation between the amount of the total dust and gas and the star formation, which we know it doesn't hold on a smaller scale. Maybe like below 50 parsec or 40 parsec. We know that Kinnicott-Schmidt relation is working on spiral scales like 500 parsec or kiloparsec scale. Well, or actually the amount of total gas is well highly correlated with the star formation, but it is not the case for smaller scale. And on the other hand, another important aspect of 21 micrometer emission is about the understanding embedded phase of star formation, which is going to last for a few million years. So what is embedded phase of star formation? This is the actually phase of star formation which has like four kind of steps. In the first steps, you have cold, dense molecular core, and after that you're gonna have embedded IR bright but optically faint emission. So you have bright IR emission, but there is no optical because all of these stars are embedded in the molecular gas and dust. And after a few million years, feedback will start and you will have breakouts and you will see IR and you will see optical emission as well. And at the end, the cluster going to be kind of cleared with the feedback, and there is no IR and it's going to be optically bright. So as you can see here, this is the part of the proposal we wrote for JWST cycle 1. This is a Spitzer map of NGC 1566 at distance of about 15-16 megaparsec. So we have HST and the MUSE VLT. As you can see with the Spitzer, with the angular resolution of about 6 oxygen, you can see much stuff here. All of the dust and clumps of massive star forming regions are kind of mixed with diffuse gas. But with the JWST, with the angular resolution of JWST, which is at the MIRI, which is at the about 21 micrometer, which is about 0.7 oxygen, which is about 10 times higher than Spitzer 24 micrometer, you can study all of these questions that I address at the distance of 16 megaparsec with the resolution of the M33 at a distance of about 870 kiloparsec. So you are going to answer a few similar questions that you ask in M33, but at the distance of about 16 megaparsec. So yeah, as I mentioned, we have a really good understanding of what are the sources bright and IR emission in the Milky Way, because it's important to understand how these different evolutionary stage of the star formation take place. So we have H regions, as I defined them, they are bright at H alpha, traces star formation up to about 4 or 5 million years, and they are also bright at radio recombination lines, like hydrogen 40 alpha or something like that. So H regions are different. Some of them they have like RC emission, rest of them they don't. Some of them are embedded in molecular gas, some of them they don't actually, and most of them actually bright at 21 micrometer, which is like this is a survey of the H2 regions in the Milky Way using WISE 22 micrometer. So using all of this knowledge that we have in the Milky Way, we understand the H regions and the stellar clusters to have different properties, and we are gonna use all of this understanding and extend it to a distance of 16 megaparsec, which we were not able to do that with WISE or Spitzer, because we don't have proper angular resolution to resolve the sources. So this is the place that we need JWST. So JWST, as you know, this is the infrared big telescope in space at the L2 Lagrangian point of the between Earth and Sun, and actually it's orbiting around the Sun. So we have it has like lots of different instruments, but more importantly here we use two instruments, which is like near infrared camera from about 2 micrometer to 7 micrometer. So we choose a few filters: F200, F300, F335, and F336. And on the other hand, we have MIRI, which is like mid-IR infrared imaging. So we only use infrared kind of imaging in this study, and there is no kind of spectroscopy. However, in the cycle 2, we propose a few new spec actually, which is like for spectroscopy, but here it is limited to the imaging. So we adopted and we choose 4 different filters from MIRI as well for a few science questions that I'm going to address in the next slides, from 7 micrometer to 21 micrometer. So F2100, which is historically quite similar to the Spitzer 24 micrometer. However, this one has a resolution of about 0.6 oxycan, and the Spitzer has a resolution of about 6.49 oxycan. So why the JWST? What are these different filters? Why we choose different filters in JWST? So as I mentioned, we have like two wideband filters in the NeoCam, specifically 200 and 360, which is going to help us to understand the obscuration view of photospheric emission from stars. And this is going to be this place. And we have 3 bands, which are, one of them is from NeoCam and 2 of them are from MIRI, which trace the pH emission, which help us to understand the pH emission and understand the size and charge and the ionization of the pH emission in the galaxies. So on the other hand, we also need to understand the dust continuum emission. That is the reason that we could request it for 21 micrometer as well as 10 micrometer. So 10 micrometer is going to also trace the silicon absorption feature in galaxies. And combination of JWST with HST, with archival HST that we have, gonna help you to understand the evolution of the stellar clusters. For instance, here in this slide, we have this kind of simulation of what do you expect from stellar cluster at the distance of 10 megaparsec if it has like stellar mass of 10 to the power of solar mass. So as you can see here, these 2 windows are JWST, MIRI, and NeoCam, and this window is HST observations. So we model the one kind of solar metallicity young stellar cluster with different dust reddening and with different ages. So as you can see here, these are color coded with the age and reddening and extinction actually, or AV. So when you have really high AV, and if they are dusty and old, you're gonna see that most of them, they are faint at HST, as you might expect. And on the other hand, if they are younger and they have like, if they are younger and I don't know, like 5 mega years, and again they are dusty, you're going to have a bright, like these emission lines, as I mentioned, pH emission lines here. So pH lines actually here. So a combination of JWST and HST gonna help you to understand the embedded phase of it as well, because those are kind of obscured and the dusty and faint at HST, but bright at 21 micrometer. So this modeling are important, and this is actually based on SIGAL that I'm going to expand on that more in the next slides. So I guess explain this. So what about the sample selection? What kind of galaxies that we choose? So we are studying main sequence galaxies, or stellar mass of about 10 to the log of 9.5 to about 11. So most of main sequence galaxies are here. So the main PHANGS target sample selection is based on zero magnitude survey, which is actually based on the 15,000 galaxies observed by Galax. They chose 19 of those galaxies color-coded with blue, and we observed all of them with ALMA. And we then limited them with HST and JWST and MUSE to 19 targets. So right now we have 19 targets at the distance of about 5 megaparsec to 20 megaparsec. All of these galaxies are spiral arm galaxies, and they are almost face on. I should say most of them are they are actively star-forming galaxies. And this red one that is color coded with red, we have MUSE observation, we have HEC observation, and JWST observations. Good news. 2 weeks ago, we heard about all of the outcomes from the JWST, and we got 55 more galaxies from JWST. So right now, until today, we have 19 galaxies from JWST, which is like these red oranges, but we requested for the rest of the 19 plus 55, which is going to be 74 galaxies from ALMA targets, that most of them are face-on and actively star-forming regions. And you will see that, and I should mention, all of these are proposals, cycle 1 and cycle 2 are treasury program. So hence they are public after observations. Right after observation, they're going to be public at MAST archive from NASA. So you can directly access and start looking at all of these gorgeous, amazing data sets. So yeah, this was about cycle 2. So right now, these, as you can see, all of these are like color composite maps of the HST plus MUSE plus optical of these galaxies. These are 19 targets that we observed so far. But this paper is based on only 4 galaxies that we observed last September, including NGC 1365, IC522, which is actually the nearest target, NGC 7496, which includes the AGN, and NGC 628, Phantom Galaxy. And I guess we observed 17 of these targets until now, and we are going to observe NGC 4255 and NGC 3351 in the next week when NASA will close the cycle 1 window. And it's going to be over. But after, like in summer, it's going to be observed the rest of the 55 nearby galaxies for us. So observations. I just wanted to share a few of these gorgeous JWST galaxies for you. This is the first target that we got right after the launch, actually, about 2 weeks after launch. And this is IC522. And this is it's like insane image. We have like lots of debates in discussion and lots of this discussion in Twitter, actually, because most of the people thought these are simulations, but not. These actually reminds of M33. This is IC522, which is like low mass kind of galaxy. Yeah, and it's color coded with different bands from MIRI. So the red bumps are these H2 regions or bright star-forming regions with 21 micrometer, and orange is like pH emission. All of this filamentary structure that you can see, filamentary structure in the galaxy that you can see is like pH, and you have like, which is bright at orange color. And yeah, I can talk about this galaxy later. And in my paper, we had, as I mentioned, we have 4 targets, NGC 7496 and NGC 628. And the most important question that we had in our paper is like, where are bright 21 micrometer emissions? So we tried to use a dendrogram algorithm, which is kind of mathematically the algorithm that is developed by my supervisor 20 years ago or something like that. And it's going to help you to understand bright peaks, actually find bright peaks at 21 micrometer. So this is NGC 7496 at distance of about 18 megaparsec. It has a stellar mass of log of 10. It has a bar and it has AGN. So, and we ran 21 micrometer peak finder algorithm to find these bright features, and we found lots. We found in total about more than 1,000 bright 21 micrometers. So these maps are false color composite maps. So the red color is 21 micrometer, green is 10 micrometer, silk color absorption feature, and blue is like pH emission from say 7.7 and 11. And we also find a few other targets, a few other peaks, as you can see here and here. So this one is like, I'm not sure if you can see properly if you're looking at this screen, but this panel showing the zoom in view of the kind of dark lane here in the spiral arc. So thanks to the FANGS previous studies, we have lots of classifications. First of all, we have H division classification from BPT diagram. We have compact cluster multicellular association classification from HST. We know where are the exact cellular cluster from NUV HST observation. We know from other studies that what is the age and what is the mass of those compact cellular population with HST. So as you can see here, these bright circles are bright 21 micrometer emission, and this red color on the background is 21 micrometer map. So as you can see, these blue squares are H divisions, location of H divisions confirmed by the MUSE VLT observations. And you can see these stars, which are like compact clusters, and MSAs stands for multicellular associations. Same thing for this kind of target, and same for these two targets as well. So first of all, we realized that the 92% of bright 21 micrometer emission is associated with H divisions, as you might expect, because most of these 21 micrometer from galaxies is emitted from recently forming OMB stars in complex of the complex of OMB stars. So this is the other two targets that I mentioned, NGC 1365, which is really saturated. All of these sparks that you can see is a pattern of the PSF of the MIRI, and it's just saturated. And this is IC 5322, which is like a kind of dwarf spiral galaxy. It's not dwarf, it's like low mass, kind of, it's not dwarf. It is like low mass spiral galaxy. So yeah. So as I talk about the peak finder and how we can classify all of these 21 micrometer emission, we have all of these sources here, and as you can see, and as I explained, as we have lots of different previous studies from FANGS, we can easily go and classify all of these sources. And as I mentioned, 92% of these peaks, these circles, are associated with H divisions, and 74% of our sources, they have association with multicellular compact clusters or compact cluster or younger cellular associations detected from HST. So let's look at a few of these regions and see what are these sources. So for instance, I've brought you a few cutouts plus SED, or spectral energy distributions. And this one at the top panel is the nu FNO, so flux density multiplied by the frequency. So these bands are the JWST MIRI 21 micrometer, 11 micrometer, 10 micrometer, and 7.7. pH, silicate absorption feature, pH, and mid-area quantity. You can see this specific source is bright at MIRI, and is also bright at HST observation. You can see this red circle, this red plus is too big, but you can see lots of bright stars. You can actually see stars here, and it's also embedded in CO molecular gas, and it has a bright H alpha feature. So we can have an initial guess. It is a solar cluster which has a solar age of about 4, 5, 6 million years, because it has H alpha. But they are sources that they are kind of bright at 21 micrometer, and as well as bright at MIRI bands. And you can see solar cluster here. It is kind of obvious in the 2 micrometer and HST band. These 3 are HST bands, but there is no CO emission here, and there is no H alpha emission here. So what is this source? What we guess that we have, but how we can model this? The initial guess is like this source, it has no H alpha. It's going to be probably older cluster with the initial guess. But in advance, I'm going to answer this question with the modeling of SED. So we have another older solar cluster here, which is bright at 21 micrometer. Almost there is no HST observation. It's totally faint at HST and optical, and there is no H alpha, but it is embedded in the CO, and it's embedded in molecular gas. So it could be older solar cluster, or it's going to be younger solar cluster. It's going to be hard to answer these questions, but I'm going to go in the next section of how we can model SED. And there are some other sources that are not interested, or actually I'm interested, but none of other people are interested. So these are some of the other targets. As you can see, for most of these targets, they are bright pH emission, 7.7 and 11. Somehow for this one, but for the galaxy itself, this is actually you can see the pattern of the SED is quite weird when you compare it to cluster. So this is the 21 micrometer feature, but if you compare it with our highest resolution observation, which is 2 micrometer from MIRI PHANGS-JWST, you can see 2 edge-on galaxy here. So this is the edge-on galaxy. This is another edge-on galaxy that is also kind of detected with HST, but it's gonna give you a false kind of hints because there are CO emission and H alpha. Hence, if you don't have a JWST emission and infrared emission, it's going to be quite hard to see if it's like a stellar cluster or something like that, and other stuff. We have other weird stuff here as well. Like it has there is no pH emission. It's like bright star of the Milky Way or bright background star actually. So which is bright at all of these bands. So the most important question is of how we can model this idea of these sources and how we can classify all of these sources with different SEDs. We have great hints and observation in the Milky Way and LMC and SMC with Spitzer and Herschel. People used Spitzer and Herschel classification, specifically ratio of different bands of about 25 micrometer to 12 micrometer to understand HBs, and 60, 25, and 12 to understand H2 regions, galaxies, planetary nebula, stars, and stars. But the point of all of these things is that all of these observations with the Spitzer and Herschel is quite limited to the LMC and SMC and Milky Way because you don't have proper angular resolution to see sources. Because the HB star, which is kind of bright at 10 micrometer, or outflow from the from the carbon outflow of these stars is kind of bright at 21 micrometer as well as 10 micrometer, but it's going to be hard with Spitzer because we don't have enough resolution. However, so motivated by these kind of ratios, we use these 2 instruments of JWST to classify sources. So based on color diagram and the visual inspection of sources, we have realized that based on the highest resolution data that we have, this is the 335 to 3.6 and 325 to 3. So these 2 bands are kind of continuum, and this band trace the pH line. So when you have bright pH emission, it's gonna be a stellar cluster. It's gonna be star forming regions that most of them they have like at this thing. So it has like as we indicated in another study of PHANGS-JWST results, that whenever you have excess of 3.3 to 3.6 or 3.3 to 3 micrometer, you will have pH emission here, and these are mostly star forming emission. But on the other hand, when you don't have pH emission, it's going to be a star, just a star, HB star, or maybe a background galaxy. We know that background galaxies, they also have pH emission, but because of the redshift, they are going to be extended to the other wavelengths, so we can observe that. Same story with MIRI actually, that when you have excess of 11 to 10 or 7.7 to 10, you're going to have pH emission. So these are bright star forming regions. And when you don't have that, it's like the star or background galaxy. And thanks to all of these rich data set of ALMA, MUSE, HST observations, we try to confirm most of these by visual inspection as well, to see if it's actually confirming our scenario. In addition, as I mentioned, to these background galaxies that are important for me, so this is a few sources that are bright at IRAC, the greatest previous telescopes that we have, with about 2.6 micrometer. So this is what IRAC observed for the background galaxies, and this is what we found with JWST 2 micrometer. As you can see here with JWST, you can see most of these sources, these galaxies are elongated spiral arms, I don't know, edge-on galaxies that you can see. But with IRAC, you can't see much. Most of these sources are classified as star forming regions in the website. But with NearCam, we can see, yes, these is our background galaxies. And I named them after our poet Hafez, and named them like HZ or maybe high Z galaxies. So I named all of these galaxies, which is like 100 background galaxies in our sample. So they right now they have a name. So the last one that you can see here, HC955, that was the I don't want to see these. Okay, you can see that edge on kind of thing that I show you in NGC 628. So what is the luminosity distribution of these sources? So if you look at all of these bright ISM sources that I am going to call hereafter ISM sources for any kind of bright 21 micrometer that has an association with H2 regions classified by MUSE VLT. So when you look at the luminosity distribution function, and if you fit a line, a simple linear line, you will see that the slope of line is about minus 1.7 from different targets in different targets, which is actually in a really good agreement with what we see from other optical studies in a few years ago. And people find out that the slope of these luminosity distribution function is about minus 1.7 for H2 regions. And we are actually, thanks to 21 micrometer, this is the luminosity of 21 micrometer, and this is the number density of the sources. And this is for every distance, different galaxy, and its color code. It's all on the top panel. You can see the stellar mass as well, using the light to mass ratio. So thanks to 21 micrometer, we are looking at a narrow range of the star formation evolutionary sequence of galaxies. That's going to help us to understand the what is the age and what is the mass, and if they are embedded in the molecular gas or not. So the most important thing or aspect of this paper is about modeling the SED. So we use SIGAL, and we included a few different modules like double exponential star formation history, dust attenuation from calcity, and dust emission from drain model, as well as nebular emission and Chabir IMF plus BCO3 stellar synthesis code to understand the stellar SED, the shape of SED actually. So these are the same SEDs that you saw in the previous slides, but right now they are modeled with SIGAL. So going through a few of these proposals and a few of these SEDs. So on the left, you can see the source that has a bright 7.7 micrometer feature, as well as 11, as well as 7. This one is 7.7, and this one is 3.3 actually. And this is the HST, and this is JWST. As you can expect, when you have like really bright 3.3 or 7.7 or pH feature, SIGAL estimated a quite old age, like 2 mega years, with high EBV and a stellar mass of about 400 solar mass. On the other hand, when you have older stellar population, which has like 21 micrometer here, and almost, you can see they have almost the same scale here. You can see the bump of the pH emission is quite fainter here. So it has a SIGAL estimated the age of about 10 mega years. So we expect here that there is no H alpha associated with this source as well, and it's going to be kind of faint at HST. But this one is not. So this is a great example of a stellar cluster, of the youngest stellar cluster and all the stellar clusters. And this is the piece that's going to be the last probably slide of my presentation, but I'm going to spend time on this one because it's the important, and it's going to answer the essential question of the Vero embedded sources. So this slide, we have on the vertical axis, we have H alpha emission corrected for dust attenuation from Balmer decrement. And on the horizontal axis, we have 21 micrometer emission. And all of these sources are ISM sources, or as you can say, they are associated with H2 regions. They are star forming regions. So the question that we had is that what is the age and stellar mass of these sources? So this plot is color coded with the age estimated from SIGAL. And as you can see here, and that it's also, I should mention that on the top, like 21 micrometer in the scale of erg per second, and this is like watt per hertz. So as you can see here, that most of sources they have like age of 2 to 5 mega years with the color of about blue, and every different symbol stands for different galaxy. And as you can see, there's a really tight correlation, about 3 order of magnitude between H alpha and 21 micrometer here. And when they are super bright at H alpha and 21 micrometer, as you can expect, they have like age of 5, 6 mega years here in the blue sources. If you have questions, that what are resources, I'm going to answer that in the end if you had that question, because I think I'm going to be running out of the time. But these are sources in the central part of the galaxies. They are going to be older, and of course bright at the 21 micrometer and H alpha. But when you have like decrease the luminosity, you will see that sources that are going to be fainter and they are going to be older as well. So in this field, you can see much more older sources with like, I don't know, 15, 20 megayear sources ages. So I should mention another thing. These symbols are also weighted by the stellar mass. So big sources, they have like stellar mass of 10 to the power of 4. Faint sources, lower kind of luminosity to mass light ratio, so it has like lower mass as well. So this red line is the median of the kind of sources that they have. All of these sources follow the same line, and which is like actually the ratio, which is based on the ratio of H alpha to 21 micrometer. But the black line stands for the ratios for the sources that the luminosity of H alpha is about 1 to the 80 of the 21 micrometer. And this vertical line is the line that we try to use to find embedded sources, or as I mentioned, they are relatively bright at 21 micrometer, but there is no H alpha emissions. And as you can see here, these sources, they are kind of about 15 or 16 sources that they are associated with CO molecular gas. And it's important here because it's first kind of direct observational evidences that we do not have bright 21 micrometer and faint H alpha. It is important. It is quite important. We know that in the center of galaxies, there could be a few sources that they are super bright at 21 micrometer and the H alpha. But if you neglect the center of the galaxies, there is no sources here. There is no super bright 21 micrometer. There is no without H alpha. And it's going to help us to understand the different phase of the actually embedded phase of star formation that when you're looking at here, it's like age of about 10 megayears, and it's going to be a good candidate for embedded star formations. But the missing piece here is that we do not have high angular resolution CO emission. We have 1 arcsecond resolution, which is like 100 parsec, which is amazing. You can see giant molecular clouds. We can distinguish all of them. We can understand the all of these free fall collapsing time, all of this stage. But at this study, we want I don't know 10 parsec resolution, and we are requesting a few ALMA deep proposals to understand if these sources they are associated with individual clouds of CO. So finally, this is my conclusion. And as I mentioned, using SIGAL, we were able to estimate the age of about 3 to 25 megayears with a stellar mass of about 1,000 to the 10 power of 5 solar mass for our sources. The luminosity function is well described by Pavel ovulation with a slope of about -1.7, and 92% of our 21 micrometer bright sources are associated with H2 regions classified by MUSE VLT observations, as well as 74% of them are associated with the stellar clusters detected with the HST NUV and the optical emissions. And we found a super bright kind of super tight correlation between 21 micrometer and H alpha, and it seems that 10% of our sources which are not in the center, and they are kind of relatively 21 micrometer faint, but super faint at H alpha, could be a candidate for deeply embedded phase of star formation. That was my end of the discussion, but I would be happy to share a few other JWST pictures that we got in the past weeks. So I shared a few of these in my Twitter pages and other social medias. This is the NGC2835 captured by JWST about 5 days ago. As you can see here on the grayscale map that you can see is HSC observation. These colors are from JWST MIRI 7.7, 10 micrometer and 21 micrometer. Same story. Red clumps are star forming regions, H2 regions, and you can see the thing with the gas and feedback wiped out the ISM and pull out all of these materials to the edge of the shell of these sources. And these are other galaxies that we observed like 3 months ago, 4 months ago. These are not published yet because we only had time to look at the 4 early targets that we had. So this is 2 other targets, and this is NGC 4303 compared with the Spitzer. So the highest resolution is JWST, the low resolution is the Spitzer Herschel. No, it's just a Spitzer actually, and almost the same band, the Spitzer and Iraq. So we can see that how it's different resolution, you can see all of this filamentary structure here. As I mentioned about the embedded phase of star formation, that most of these sources are deeply embedded in the gas and molecular gas. I can talk about this one if anybody is interested. And we are looking at we need a high resolution, near cam resolution matched of about 0.5 oxygen to see the embedded phase of star formation. As we can see, all of these slow associations are located in the bright CO features. And finally, this slide is going to be probably more interesting for Juan, as I mentioned in the beginning of my chat with him. So this is another aspect of my PhD, which is like observing astrosat, observing UV from astrosat. So this is the PHANGS atlas of nearby galaxies at UV bands. So these blue colors that we can see are about FUV kind of maps band, and the red and the yellow color is NUV, and the red contours are from CO molecular gas, and the orange footprint are from MUSE VLT observations. So this is another amazing aspect of astrosat, that we can look at the galaxy with the spatial resolution of with angular resolution of about 1.5 oxygen, 3 times better than galaxy. I'm going to stop here and keep the floor for other people to ask questions, and maybe about astrosat or any other of these things. Thank you so much.
Thank you very much. Thank you very much, Hamid, for the really nice talk. And you have impressive images to show. So, questions? I will start with a question about the modeling that you performed with SIGAL. I realized there are some of the regions in which you detect a source in HST, and then also a source in James Webb, and they have a counterpart in CO. I would tend to think, so do you think you are seeing the same source in every one of them, or in the optical you see one part of the young cluster population that have already emerged, and then at 21 micron, maybe you see the center of the molecular cloud where new regions are forming. So when you model this with SIGAL, does everything comes from the same source, or you have a mix of different things that are spatially in the same location?
That's important question actually, because first of all, I should about the first question that you asked about CO. Our kind of resolution from CO ALMA is limited, so we have 1 oxygen resolution, and here we can see, so all of these maps are aligned together, so you're looking at exactly the same region. And as you can see, this bright feature at 21 micron is associated with lots of bright CO feature here, but because of the low resolution CO, we cannot disentangle between the diffuse emission and the source emission. So that is the main aspect of the CO. On the other hand, for your second question, that if we have like other kind of emission, we have done background subtraction, not the background subtraction for the noises and the background for, like, I don't know, for all of these things, but we kind of consider circles and around our sources, and we subtract like 2 or 3 pixels beside all of these sources, and we are looking with and all of these maps, actually, it's important as well to mention, all of these maps of HEC and JWST are convolved to the same resolution of JWST MIRI, to the 0.6 oxygen resolution. So we have almost all of them are convolved to the same resolution, and as we are doing background subtraction of the around circles, we are almost looking at the same source. However, because of lower resolution of the MIRI in comparison with the HST or the JWST new cam, it's going to be combined with with diffuse emission as well. So yeah, that's the idea. But regarding your first question, yes, for specifically this one, that is I mentioned this as a young cluster because you have like bright feature of the pH. It is also associated with the stellar clusters, but it's also like included in the clouds in GMC. Most of these are classified from Erik Kozlowski paper. That is like they are GMCs, but because of the resolution, we cannot actually see if it's one cloud or two clouds. And the main point from SIGAL, as you know probably, we cannot include any information from SIGAL from CO emissions. So just like we included just JWST and an HST kind of bands to model the SCD.
Yeah, but for example, when you model this with SIGAL, SIGAL does this kind of energy balance thing. So if you add a young stellar population and then extinction, then SIGAL is going to reproduce or is going to try to fit the mid-infrared emission as the energy absorbed in the optical and then reprocessed in the infrared. So this works if what you see is the same thing in all the bands. So if you see one stellar population that it's emitting and it's obscure at the same time. But if what you see is a young source or a young cluster, and then another part of the cluster is obscure, then with SIGAL, this is going to be more difficult to fit, because if you have two sources unresolved, SIGAL is still going to try to perform this energy balance. So that's why I was asking this, because maybe what you see at 21 micron is not the same source, and not the same stars as those emitting in the optical trial.
That is totally right. Yeah, that is the problem of the when you are looking at the 21 micrometer, and if you want to limit your study to 21 micrometer resolution, your point is totally right, because you are losing resolution and you have like 2 or 3 or 5 stellar cluster. Part of this cluster are young, part of this is old, and SIGAL maybe mix all of these, which will does, because you are giving a mixed information of all of these sources when you convert all of this information. However, in another paper of our FANGS, which we only focus on near-cam data, which we only focus on the highest resolution data, or 0.1 oxygen, on that study, we can understand the stellar cluster ages more kind of with more details, as we can see individual stars. So in this paper, which is like mostly more important for like classification and initial ideas, initial guesses about ages and mass, you're right, we are totally limited to 21 micrometer, and we are giving mixing kind of mixture of the diffuse gas stellar clusters, younger stellar clusters, and older stellar clusters. And it's going to be probably the case for the regions that you have lots of stellar cluster, like a spiral lines. You have lots of a crowded vision of stellar clusters together. But in the case of isolated stellar clusters, it's going to be probably much easier. But the main idea of this paper is like giving information of where are the 21 micrometer sources and understanding embedded phases more, focusing on the lowest resolution. I mean, 50 parsec, 40 parsec, 30 parsec, because at the DC distance, we are looking at the 30 parsec to 50 parsec. However, with the near cam, you can see 5 parsec or 2 or 3 parsec. So yeah, you're right.
Okay, thanks. Now,
Thank you.
we have a question from Antonio. You can see him there.
Hello. Nice talk. My comment was a comment on the comment by, So I agree that it could be complicated with SIGAL to account for this obscure population, but since he's modeling individual cluster, maybe, and he's using 2 exponentials, maybe one of them is modeling the unobscure population, and another one can account for whatever emits in the infrared. So it would be interesting.
But what SIGAL does not do, so SIGAL can model 2 populations
with different extinction.
But he tends to use one young and then one old, not.
Yeah, but in this case,
too young. But yeah, you
have both of them could be young, and one of them is.
Yeah, and you can use that to decouple the. Yeah, that's okay.
I think I did not mention that properly. That is the case here. We included double exponential star formation history model in SIGAL because you can use single stellar population with one specific age, or as you mentioned, you can use different ages to allow SIGAL to look at the different bands with HST and the different pH bands to understand the ages. But yeah, we included the double exponential star formation history in this paper. However, in the other papers that people studied, look at the high resolution data, they only included the single stellar population thing. And yeah, that's the case. Maybe I didn't really, I was super fast in this slide. So yeah, we included the double exponential star formation here.
I have another comment related to this. So you are modeling individual sources, but have you considered modeling all the spatial resolution elements to get maps of parameters like the extinction, the age, the metallicity, and so on?
So I guess you are kind of meaning that doing that by pixel or something like that? Am I right?
Pixels or group of pixels, whatever, but to get maps that cover the entire.
That is right. Yeah. So it's a long story. When we got the data, it was like 2 or 3 months after the launch, and we worked on this project from like, I don't know, from like 1 a.m. to the rest to the 1 a.m. of the next day. So it was a really, really compact time because we wanted to start to pushing our compact to the literature. And I had like other things as well. We had 21 papers and we had like lots of different papers. Like one of those papers like 15 pages if you're looking at Adam Leroy paper. But yes, this study is going to be extended to a bigger study, which include 19 targets. And we are thinking of including astrosat data, UV, as well as maybe providing maps of these sources, because Medric, his last name is in Chile, in Spanish, I don't want to pronounce that. It's kind of hard for me. He's in our collaboration, the person who builds the SIGAL. And we had a great discussion with him last time about this, because he also published a map of, maybe you saw that paper as well, like a year ago, a map of age and mass of solar population in NGC 628, mostly focused on the UV data. But yes, that's one of my initial things that we had, like using JWST, HST, and astrosat at 2 oxygen, we can do the SED fitting pixel by pixel for Galaxy as well. This could be this is an excellent idea, but we need time.
Okay, thanks a lot.
Thank you.
Now, Mohammed.
Yeah, thank you very much, Hamid. Do you hear me, or should I let me just compare the cameras on?
That's perfect.
I had 2 questions. I'll try to keep it short so we can finish. One of them is are all the MUSE FANGS galaxies also now observed with JWST? That was what your Venn diagram suggested, but I just wanted to.
So from 19 galaxies in cycle 1, we observed 17 galaxies. The other 2 targets going to be observed by the end of 2 weeks.
These are the MUSE FANGs that are observed by JWST.
Yeah.
Okay.
19. Yeah.
Okay.
For those 19, we have JWST. For those 19, we have 17 JWST, 19 MUSE, 19 HST, 19 astrosat, 19 other.
Okay, thank you. So, and another fast question about essentially the dendrogram segmentation that you showed from your advisor. I wanted to see, have you studied the systematics of that kind of detection? So, for example, are there certain morphologies of these clumps that can be missed? Or are you biased to detecting more, certain types of morphologies in these regions? And if that can affect your final result in the final plot where you showed the relation between the near infrared flux and the H alpha flux. So essentially the relation, where morphology falls into this. Have you studied the effect of morphology?
So I guess most of as for when we are looking at these sources, we are looking at the PSF size of the JWST or 0.6 arc scan resolution. So most of these sources are unresolved, so you don't see any kind of stories inside that. And yes, you're right, they have different morphology. They can be mixed with the diffuse gas in the spiral arms, or they are located in the dust lanes. But in an initial part of our study, we also try to find the finding peaks using extractor and the dwarf as well, and we found kind of 90%, 95% match as well, because the dendrogram actually just looking at just find the peaks properly, and I would say there is no specific kind of biases as far as we compare that with dwarf or extractor. I'm pretty sure that you are more expert in this area more than me. But in the case of the 21 micrometer relation with H alpha, I don't think so, because these are essentially super bright sources at 21 micrometer and H alpha. And when we compared our maps to the location of peaks and we look at the regions, it seems the peak finder algorithm is working well in finding the peaks. And I would say there is almost small effect of the morphology of the regions in this relation.
Okay, thank you very much. Really nice talk.
Thank you.
More questions? I have another one about the luminosity functions. Can you show the figure with the luminosity functions for different galaxies?
Sorry, I didn't hear that well. The peak finder?
The figure, the slide with the luminosity function.
Oh, luminosity function. Yeah.
Exactly. So you find very similar slopes, but I noticed that, for example, in 1365, you have a population of very bright sources compared to the other ones.
Yeah.
What are those sources that are between 10 to the 20 and 10 to the 22? Are they also very massive star clusters? Because that would change that would introduce like a broken power law slope or something like that.
That is right. Yeah, that's super important question actually. We see a biomedal kind of distribution here in NGC 1365. That is because of the nuclear part of this galaxy, which has super bright AGN. I didn't mention exactly that we kind of mask the bright saturated PSF part in the center of the galaxy, and we mask all of these bright sources, bright region of the galaxy, bright central part of the region of the galaxy. But still, we have a few bright sources that they have like a stellar mass of 10 to the power 6, 10 to the power 5 actually, as it's also confirmed by the Brad Whitmer paper in the PHANGS-JWST targets. So these are bright sources in the center, as you mentioned, and yes, it seems they have like different luminosity function, but we try to kind of look at just the most of the I don't know 69 percentile of the data which lies here. So these are regions that they are, I would say, more in the galaxies. So yeah, you're right. These are super bright 21 micrometer massive stellar clusters in the center of the NGC 1365 around the AGN.
Okay, and the last question: Do you plan to observe some of the region with MIRI IFU to do a spectroscopy, or MIRI spec?
Yeah. Can I say that? Yeah, I guess proposal are public now. So we requested one specific for a part of NGC 628. I'm afraid I'm not sure if that proposal confirmed or not, but we requested for MIRI actually IFU with MIRI, not MIRI spec of this chunk of the galaxy, 1 kiloparsec size of the galaxy. I think one of these proposals got accepted, but I do not remember exactly if that was if was this case or not. But we don't, for the cycle 1 and cycle 2, most of these most of our efforts are based on imaging, not in MIRI spec, or not based on spectroscopy. But I'm just trying to remember because my supervisor, he also got some field of M33 with NeoCam and MIRI, but it was also imaging. Maybe, I guess.
because it will be very exciting to see the infrared spectrum at this resolution of some of these bright infrared clouds.
Yeah. We know that there are lots of difficulties with like NIRI-SPEC and the MIRI, I feel, because there are lots of difficulties with the instrument, as far as I know. But if we wrote 2 or 3 proposals, but I do not remember the exact outcome. I know that we got data for NGC 253, a NIRI-SPEC, NuCam, and of course 55 pneumonia galaxies. But I'm not super sure about the spectroscopy data. I can update you on that matter and send you an email.
Okay, thank you very much.
Thank you.
So if there are no more questions, we thank you again, Hamid.
Thank you so much.
And you are welcome to visit us. He mentioned that he will come to Spain in 2 weeks. So
Yeah.
You're welcome to visit us whenever you come to Spain.
Yeah, thank you so much. Yeah, I will visit a few universities, so Valladolid and Madrid and OAN, an institute in Madrid. I do not remember the exact name, but maybe I will someday see your great institute as well.
Okay, thank you very much.
Thank you as well. I'll say thank you, Sepida, as well for all of these things that she done to facilitate all of this process.
She's there.
Yeah, I can see something. Yeah.
Okay, let's stop
Great.
recording.